Welcome to the video on Simple Harmonic Motion or SHM. In this video, I'm going to cover what does it mean by an oscillation. Then we will see what's the mean or the mid position and the extreme or the endpoints. And then we are going to cover the displacement and amplitude. And then I will be defining the time period. Also, the most important part will be explaining the equation for the displacement and then drawing the displacement time graph. Subsequently, I will be covering the equation for the velocity of the object executing simple harmonic motion, and then I will be explaining the velocity time graph. And finally, we are going to see the equation for the acceleration of the object, and we will also study the acceleration time graph. I'm going to explain this concept, all the terms and equations and the graphs with the help of the setup. The setup consists of a system of a spring, and we have the object on one side attached to the spring, and the other side of the spring is attached to a wall, for example. And this object is resting on a frictionless surface, and there is no air resistance. So what happens when we bring this system into executing simple harmonic motion by either stretching it or by compressing it and then releasing it, and then trying to understand the 4 different quarters of one cycle of simple harmonic motion. So let's start. Let's understand simple harmonic motion. One of the most simple and interesting ways to understand simple harmonic motion is through the motion of an object attached to a spring. So let me first take you through the setup. On the left-hand side, I have shown there is a spring, and one end of the spring is attached or fixed to the wall, and the other end of the spring is fixed to a block of mass m, and this block of mass m is resting on a frictionless floor. Okay, and we also assume that there is no air resistance. Now let's say the point O represents the origin, and the point A represents a position at a distance of A units to the right, which means the maximum position at which the object M will go when in motion. And similarly, point B represents the position minus A. So let's say the object is at rest. If I have to make this object execute a simple harmonic motion, then all I have to do is pull the object towards the right. And let's say I bring it till the position x equals to A, and then I release the object. As soon as I release, due to the restoring force of the spring on the object will move towards the left-hand side. It will touch the point O, and then it will continue to move till the point B, such that x equals to minus A. And it will continue because of the restoring force again. It will move from point B to O, and then again O to A. It is observed that the object will execute simple harmonic motion infinitely, which means it will, let's say, go from A to O, and then from O to B, and then again B to O, and then O to A. Now, what we mean by one cycle of simple harmonic motion is you take any starting point, let's say A, and then you have to touch the other endpoint and come back to the same original starting point. So that is one cycle of SHM. So while the object is continuously executing simple harmonic motion, let's understand in terms of the displacement and the time period, one complete cycle. So I have, for the purpose of understanding, I've taken the reference figures as 1, 2, 3, and 4. And I have taken the reference or the starting point as the point O. So let's say at time t equal to 0, the object is at the origin, and it moves towards the right-hand side, and it covers a displacement of A in a time given by time t equal to t over 4. So t here refers to the time period, which is the time taken to complete the full one cycle of SHM. And in figure 2, we see that the object starts the motion at time t equal to t over 4, and at the end of time t equal to 2t over 4, which is half of the time period, the object covers a displacement of negative a. Why negative? Because it is moving from right to left. Yeah. So we see that in figure number 3, the object continues to move towards left. So which means it starts at t equal to 2t over 4, which is again t over 2. And at t equal to 3t over 4, it reaches the point B. Yeah, it covers a displacement of negative a because it is still moving from right to left. And in the last part of the one cycle of SHM, in figure 4, it starts at time t equal to 3t over 4, and it covers a displacement of a because it's positive because it is moving from left to right. And at the end of time t equal to 4t over 4, which is nothing but t, it comes back to its original starting point O. So to summarize, this is the first part of the cycle, or 1/4 of the cycle, and this is the second quarter of the cycle, and this is the third quarter of the cycle, and finally this is the fourth and the final quarter of the cycle. So when I say cycle, it is one oscillation or one simple harmonic motion. And as you would have seen, time t is the time it takes for the object to complete one cycle of SHM or one oscillation. Yeah. So let's recapture some key terms. Displacement. Displacement refers to the change in position of the object, and displacement is considered as positive when the object is moving from left to right, and negative if it is moving from right to left. Then the next term is amplitude. So amplitude is represented by the letter A. Amplitude represents the maximum displacement the object will have when executing simple harmonic motion. So amplitude will be plus A on the right hand side, and it will be minus A on the left hand side. Now in this slide, I'm going to discuss the equation for displacement in simple harmonic motion. So just a quick recap from the previous slide. What is a simple harmonic motion? That's the to and fro motion of an object about a mid position or central position. We are going to consider the motion of the object from the point O to point A. That means moving towards right. Part 2, in which the object moves from point A to point O. And part 3, in which the object moves from point O to point B. That means towards the negative x direction. And finally, in part 4, the object moves from point B to the point O. So if that is the way we define simple harmonic motion, summarizing again, that is to and fro motion of the object about a midpoint, and such that the displacement on both the sides of the midpoint is the same. Also, that each part of the motion will take 1/4 of the period. So O to A, and then A to O, and then O to B, and then B to O. Each of them will take time equal to T by 4. Now, given these conditions, can there be an expression or equation for the displacement such that we substitute the values for time in that function? It will truly represent the displacement that we observe. So one such equation can be x equals to a sine omega t. Let's consider the equation x equals to a sine omega t and analyze if indeed this function or the graph represents what we observe for an object to be executing simple harmonic motion. So when the object is at the central point O, so we assume that will be a sine omega t, which means sine 0, and sine 0 is 0. So displacement will be equal to 0. So at this point O, the coordinates will be 0, 0. Therefore, the displacement x equal to 0 matches with what is given to us. This is the starting position, point O, also represented at time t equal to 0. So maybe this I can call it as 1/4 of the cycle represented by 1. Now let's consider the object to be at A. So at time t equals to t over 4. So we are talking about the point A here. And let's see if the time is represented as t equals to t over 4, then what's the displacement we get from this function? That will be equal to a sine omega, which is 2 pi over t, times t over 4. So t and t cancel, 2, and here it will be 2. So this will be a sine pi over 2. And we know that sine 90 degree is 1, so that will be equal to a. So I can write the coordinates of the point A as t over 4, comma a. And we see that x equals to a indeed matches with what we observe in the case of a particle executing simple harmonic motion. We see that the displacement is a, and therefore this function helps us so far to confirm that it provides displacement values in accordance with the observation for a simple harmonic motion. Let's now talk about the part 2, the second quarter of the cycle, when the particle is moving from point A to the central point O. Yeah, the object is at point O at time t equals to 2t over 4. So we're talking about this point O, and let's see what is the value of x we get from the function. So at time t equals to 2t over 4, which is t over 2, what's the value of x we get? So x will be equal to a sine omega 2 pi over t times t over 2. Yeah, so 2 and 2 cancel, t and t cancel. So sine 180 sine pi is 0. So that will be equal to 0. And therefore, the coordinates of this point over here will be t over 2, comma 0. Now, which in turn definitely matches with what is the expected behavior of a simple harmonic motion. So displacement is supposed to be 0 at time t over 2. Let's see now the third quarter of the cycle, where the object is moving from x equal to 0 to x equal to minus a. So we're talking about this point, and in terms of the third quarter, so I can write it as third quarter. So we're talking about the point B. Maybe I can write this also as point B. And let's see, at time t equals to 3t over 4, what is the displacement we get? That will be equal to x equals to a sine 2 pi over t times 3t over 4. T and t cancel, 2 and 2 over here. So this will be a sine 3 pi over 2, or 270 degree, which is minus 1. Therefore, it will be minus a. So which matches with the observation that the particle or object will be at position x equals to minus a, and which in turn also we can write the coordinates of this point as 3t over 4, comma minus a. And now let's see the final quarter of the cycle. So when the particle is coming back from B to the central point O. Yeah. So it is happening at the end of the period T. So this is our fourth quarter when the object is moving from B to O, and at time t equals to 4t over 4, which is nothing but t. Let's see what is the value of x. So x will be equal to a sine omega, which is 2 pi over t times t, and sine 2 pi or sine 360 degree is 0. So that will be again 0. And the coordinate of this point will be t, comma 0. So which in turn is matching with the observation we have in case of simple harmonic motion, that at the end of the time period t, the object is expected to be its original position. So let's spend a few seconds to summarize. So if an object is executing simple harmonic motion, then its displacement can be represented by a function with respect to time given by x equals to a sine omega t. And in such a case, omega will represent a given by 2 pi over t, where t refers to the time period. Let's see now the equation for velocity of the object. So we need to analyze if this equation x equals to a sine omega t is good enough to also give us a calculation for the velocity, and whatever value we get from this function for the velocity should match with the practically observed value. So again, I've drawn the graph, but before we go into the graph, I need to explain that velocity is the time derivative of the displacement. So it is d by dt of x. So which means it will be d by dt of this function a sine omega t. Omega is a constant given by 2 pi over t. And a is also a constant, so I can take a out, which is the amplitude. So a times d by dt of sine omega t. And this will be equal to a times derivative of sine omega t is cos omega t times d by dt of omega t. So as I mentioned, omega is a constant, so this will be eventually equal to omega a cos omega t. So what we understand from this is the velocity of the object executing SHM will be represented by a cosine curve. So I have plotted the cosine curve in figure 4, and I have also captured figure 1 and 2 as a reference. So let's analyze for each quarter of the simple harmonic motion. So starting from point O, when the object is moving from point O to A, represented by this time period and represented by this displacement at that time, at point O. So time t is 0. So at time t equal to 0, what is the velocity? Velocity will be given by omega a cos 0. And we know that cos 0 is 1, so this will be equal to omega a. And therefore, for the position O, the coordinates will be 0, omega a. So that is also the maximum value of the cosine curve. And this is also the practically observed value at the main point, midpoint O. The velocity of the object is the highest. So far this function complies with the observations of the simple harmonic motion. So I will call this as first quarter of the cycle of simple harmonic motion. And when the object reaches at point A, when the object is at point A, that means at the end of t by 4. So if I put t equals to t over 4, and I see what is the velocity. So velocity will be equal to omega a cos omega, which is 2 pi over t times t by 4. So t and t cancel. This is 2. So this will be 2. And cos pi by 2 will be 0. So we get the value as 0. And therefore, the coordinates of the point A I can write as t over 4 comma 0. Now, does it match with the practical observation? Yes. It is seen that when the object is at the extreme position on the right-hand side at point A, before it starts moving towards the left-hand side, at point A, momentarily, the velocity of the object will be equal to 0. So that is in agreement with the practical observation, and therefore the function gives us the correct value of the velocity. And in the return path from A to O, let's say, which is the second quarter of the cycle, in the return path, the object will be reaching to the mid position, point O, at time t equal to 2t over 4. So at point O, when it has reached after a period of t by 2, so we can write t equals to 2t over 4 or t by 2. Let's see what is the velocity we get. That will be equal to omega a times cos omega, which is 2 pi over t, times t, which is t over 2. T and t cancel, 2 and 2 cancel. So cos 180 is minus 1, so this will be minus omega a. Similarly, I have done the calculations for the subsequent points O, B, and again O. And you can verify these calculations on your own. And it is seen that at point O, at the end of the velocity is maximum, but in the negative direction, which is as observed in the case of object executing SHM. And then at the end of the quarter 3, that means at the extreme point B, the velocity is expected to be at this point B, the velocity is expected to be 0. And at the end of the fourth cycle, that means when the particle is at point O, the velocity will be the maximum. Again, it will be positive maximum because the particle is moving from left to right. So overall, we conclude that the expression x equals to a sine omega t also correctly gives us the expression for velocity given by omega a cos omega t. Let's now finally understand the equation for acceleration of the object executing simple harmonic motion. So previously we have seen the equation for the displacement and also the velocity given by x dot or x dash or v. And now time to understand the equation for acceleration. So acceleration in simple terms is defined as d by dt, or differential with respect to time of the velocity. So this will be given by d by dt of v, which is given by omega a cos omega t. And we know that omega is a constant given by 2 pi over t, since t is constant. So therefore that can be taken out. And we also know that a is a constant. So both of them can be taken out. Omega times a times dy dt of cos omega t. So that will be negative sine omega t. And finally, applying the chain rule, we have to do dy dt of omega t, which will be omega. So if we rearrange the terms properly, I can take negative sine out and then omega square a sine omega t. Now we know that a sine omega t is nothing but the expression for the displacement, and therefore I can write it as minus omega square x. So that's one very important equation you need to remember. And now let's try to understand the graph for the acceleration. So if on the x-axis we have the time t, and on the y-axis we represent the acceleration. So let's see at different points what are the values for the acceleration. So on the left hand side, where the figure remains the same, we have simple harmonic motion represented in steps 1, 2, 3, and 4. Yeah. And let's see at time t equal to 0. So at time t equal to 0, acceleration will be given by minus omega square a times sine omega t, and t is 0. So acceleration will be equal to 0, which means coordinates of this point will be 0, 0, which means it's representing this point. Yeah. It's representing the midpoint when t is equal to 0, a is equal to 0. And I've given x for reference. Yeah. So let's see the other point at point A. When the object is at point A, that means after a time t equal to 1t over 4 has passed, what is the value? So when time t equals to t over 4, what's the value of acceleration? So that will be minus omega square x, which is a sine omega t, and omega can be written as 2 pi over t times t over 4. So t and t cancel. This will be 2, and this will be sine pi by 2 is, we know it is 1, so it will be minus omega square a. And that's what we have this point A representing. So the point A is representing t over 4, comma, minus omega square a. Okay. Now the particle will start moving from position A to the center point O, and at time t equal to 2t over 4, it will be at position O. So let's see at time t equal to 2t over 4, which is nothing but t over 2. Value of acceleration will be minus omega square x, that is a sine 2 pi over t times t, which is t over 2. So t and t, 2 and 2 will cancel, and we know that sine 180 is 0, so that will again be 0. Yeah, so I can mark the coordinates of this point as 2t over 4, comma 0. So after this, it will be moving from the position O to the position B, which is represented with this, step number 3. And at time t equal to 3t over 4, it will be at point B, so which is represented over here. So let's see, at time t equal to 3t over 4, what's the value of acceleration? So acceleration will be minus omega square x, and x is given by a sine omega, which is 2 pi over t times t, which is 3t over 4. T and t cancel. This will be 2 in the denominator, and we know that sine 3 pi by 2 is minus 1. So minus of minus will become plus, and therefore this will be plus omega square a, and that is what is represented by this point. So I can safely write this as 3t over 4, coordinates of this point, omega square a. And then finally, when the object is moving back from the point B to the midpoint O at the end of time t equal to t, which is this one, we need to find what's the value of the acceleration. So if I put t equal to t, then acceleration will be given by minus omega square a sine 2 pi over t times t. So t and t cancel. Sine 2 pi is sine 360, which is again 0. So this will be 0. So I can write the coordinates of this point as 40 over 4, comma 0. So if I summarize, the acceleration of the object executing simple harmonic motion is positive maximum at point B. So, and it is negative maximum at the point A. So at the extreme points A and B, the acceleration is maximum. And at the center point, it is minimum, and that is equal to 0. So for all the points O, you can see the value of acceleration is 0. In the subsequent video, I'm going to provide a comparative view of the displacement, velocity, and acceleration by studying all three graphs at one place. And also we are going to see what are the minimum and the maximum values, and if the values are increasing or decreasing while executing certain part of the one cycle of simple harmonic motion. Let's try to understand why do we get particular values of acceleration on the extreme points and also at the center point. So springs have a property wherein the spring applies a restoring force, which is a force exerted by the spring on the object to bring back to its original central position, is given as minus k times x. Yeah. So k is known as the spring constant and x is the displacement. So what we are saying is, if you try to stretch the spring, for example, it is at rest in figure 0, and if we pull it by the displacement x, then the force which the spring is exerting on the object trying to bring it back to the point O is directly proportional to the displacement. So one thing is very clear: higher the displacement, higher will be the force. Okay. Another thing is there is a negative sign over here. That means force will be acting in the opposite direction. So if we see all the forces which are acting on the object in the horizontal direction, so that's known as the free body diagram for the mass m. So there will be a force. I'm interested only in the horizontal forces right now. So there will be a restoring force. And how about this? Will there be a force which is going to oppose, like force of friction? Will we have this or not? So assumption I have taken as it's a frictionless surface. So this force will not be present. And therefore, the net force which is present on the object is only Fr. So in terms of the net force, let's see, F net will be equal to sum of all the forces. So Fr towards the left minus if there was a force of friction. Since there is no Ff, so I can make it as 0. So F net will be equal to Fr. Yeah. Therefore, we from Newton's second law, we have the expression F net will be equal to mass of the object times the acceleration. So if I combine the two equations, I get F net, which is equal to Fr, will be equal to m times a. Yeah. So if the restoring force will be high, which is at the extreme, then the acceleration will also be high. So that's the reason acceleration is always high at the extreme point. So let's say we talk about point A. So here x is the maximum, x becomes equal to a, and therefore the restoring force will be the highest, and therefore acceleration will also be the highest on the right hand extreme point. But if we move towards the left point, yeah, so if we move towards, let's say, figure 3, which is at point B. So at point B, x becomes negative, yeah, because it is pointing towards left. And therefore, the restoring force will act towards the center. Yeah, and again, restoring force will be the highest because of the maximum displacement, which is negative a. So displacement is negative, pointing towards left. So this is negative x, and therefore restoring force, which is I have to also write the expression, the restoring force equals to negative kx. And since we know that restoring force is negative kx, so minus of minus will be plus, and therefore restoring force will be acting towards the center, the point O. So it's very important to understand why the acceleration is maximum at the extreme points. And now let's also consider the center point. Center point O, we have the displacement is 0, and therefore the restoring force is proportional to the displacement, will also be 0, and therefore the acceleration will also be 0. So at the center, acceleration will always be 0, and at the extreme points, it will always be maximum, and opposite to the direction of the displacement.